What are we talking about? So we're talking about the idea. So let me just remind you, so you can, you can all see from me from here. I'm just going to write some very basic stuff. So the idea is you have random variables, x1, x2, xn, and they are IID, random variables, and they have a mean, and the expectation of xi is typically mu, and the variance of xi is typically sigma square. We're assuming these are numbers, okay? And the idea is that we are trying to construct on the basis of realizations of this sample. So we have these random quantities, and we have this then realization x1 or 2xn, which are a sequence of real numbers which correspond to data associated to these real values, these random variables, and what we're trying to do is on the basis of these observed values to try to, for example, estimate the mean value of the random variable xi, which corresponds to an independent identically distributed copy of a population random variable of interest, or for example estimating the variance, or estimating associated confidence intervals or intervals associated to these quantities. Now, what we were doing at the end of yesterday's lecture was looking at the idea of constructing an interval for the mean of these random variables in the scenario where we had a collection of IID random variables which are representative of this model, and we knew the variance and the number of data points was large. So if you remember where we finished off yesterday, so there was an example, but basically where we finished off yesterday was that the notion that, no, this is the error part, sorry. The notion that basically an interval, 1 minus alpha 100% confidence interval for this population mean mu, where basically the data are a random sample which are either Gaussian or the sample size little n is large, and we knew the variance somehow of the associated sample looked like this, okay, where these coefficients z of alpha upon 2, we were getting them from the Gaussian tables. Okay, and alpha is a level of confidence. Obviously, the closer alpha is to 0, the more confident we are that the true value lies in this interval, because basically the probability that the mean parameter mu lies in this interval from the beginning is equal to 1 minus alpha. Okay, and these are all, these type of results, as you remember, are all based upon those Gaussian type results that we looked at in the previous chapter. So that was in the case, that was the case where we knew the sample variance of the random variables of the population, which may not be the case in general. Okay, so what we're going to do is now to construct a confidence interval in exactly or almost the same way as we did before, except of course, sorry, of course now what we're assuming is that the underlying sample variance of the associated random variables is now unknown, which is of course a much more reasonable type of assumption. So we don't know that variance, and we're assuming that these xi's are, let's say they're normal or very close to normal. Okay, well, let's say they're normal, really. I don't like saying very close, and closed is the close, of course, not closed. Let's say they're exactly normal, so we don't have to say anything too silly. And the number of data points, little n, or the number of replicants, is going to be small, so less than 30. Okay. Right, so this is the scenario where one will try to use this type of procedure. Okay, so we define a statistic capital T, which is the sample mean minus the population mean, which we're trying to compute an interval for, divided by the square root of the sample variance divided by n, or if you like, square root of n on the bottom. Okay, so we know something that we talked about just in yesterday's lecture, and basically it was a result quoted from this chapter 5, that this statistic, when these random variables are exactly Gaussian, is distributed as a t distribution on n-1 degrees of freedom. So the logic being that basically this numerator is Gaussian, and is Gaussian, and this denominator is roughly chi-squared. I mean, this is approximately the justification here. So remember, the ratio of a normal 0.1 random variable to a chi-square root of a chi-square of its degrees of freedom gives you precisely a t distribution. This is very roughly the logic that we had before. Okay, so the key point is now that we know under our assumptions this random variable, where the random Okay, sorry about that. Where the randomness is in the data, this thing is precisely a t distribution on n minus 1 degrees of freedom, where it is explicitly a function of the unknown mean that we wish to provide an estimate for. And so just as we did in the case where we had a known variance, we can construct this 1 minus alpha 100% confidence interval in a very similar fashion. So there's a collection of calculations which are very much analogous to the ones that we looked at yesterday. So just to think about the first line, just for you to be clear. So once we have the first line, the rest of it is pretty straightforward. The whiteboard doesn't work properly. So basically, remember that these quantiles, if you like, of the t distribution. So this is t and n minus 1 alpha on ton. So what does this first statement mean? Well, it basically means the following. So if we plot the t distribution as well as I can, so we have this axis, let's say t, this is his PDF ft of t, and then basically the PDF looks something like this. Then what this equation on the left-hand side at the top of the exposition, i.e. this one, what it says is basically these points. So this is a t, so here t is distributed a t on n minus 1 degrees of freedom. So this point is minus t alpha over 2 n minus 1. Or is it? It's the other way around, sorry. Tn minus 1 alpha over 2. Alpha 2. This point here is t n minus 1 alpha over 2. And this two probability, these two areas are supposed to be alpha over 2 respectively. Okay, this is what this first statement means. So these 2 points, again, Tn minus 1 alpha over 2, Tn minus 1 minus Tn minus 1 alpha over 2, represent basically the tails points of these probabilities. So I've written them right in the tail because typically alpha is very small. Okay, so basically, if those two areas are alpha over 2 respectively, the probability in the middle, which is essentially the shaded region, is 1 minus alpha. Okay, so now what do we know? Well, we've defined t to be is equal to x bar minus mu over s over root n. Okay, so this first statement is exchangeable with the second. Okay, and now we're just doing standard calculations. So we just take the s over root n, we multiply the inequality by s over root n is positive, so we get like this. Okay, then we subtract the mean and we multiply it by minus 1. And basically now the mean mu, which is not a random quantity, so this is a randomness in the data, not mu, okay, but the probability that mu lies in this interval is precisely 1 minus alpha. Okay, it's precisely these exactly because we have the hypothesis that this statistic t is precisely t distributed. So that's very good. So now, so the point is, so basically x bar is the mean, s is the sample standard deviation with the ratio n minus 1, and the random sample of size is less than 30. What does it say? An approximation. Okay, so basically, then basically the confidence interval under our, let's say they're normal, I don't like saying approximate, then basically this is our confidence interval, which is x bar plus or minus t on n minus 1 alpha over 2, this is from the table, times s over root n. Okay, so this one we will get from our table that we have looked at yesterday. Okay, but what if n is large? Okay, so if n is large, basically we know that the t distribution, if you remember when we introduced that last week and we discussed about it yesterday, is the number of degrees of freedom little n goes very large, then basically the t in the normal is almost indistinguishable. In fact, for n is 30, if you drew the densities, they should look very close, one hopes. Okay? So the key point is, even when sigma squared is unknown, okay, if sigma squared is unknown and the number of data points n is quite large, 30 apparently, then a 1 minus alpha 100% confidence interval is basically the same thing for the mean parameter mu, is essentially the same thing. The only difference is that essentially instead of this t on n minus 1, we're basically replacing that with the quantiles of this Gaussian distribution. Okay, the point being that this z alpha over 2 and tn minus 1 alpha over 2 are almost indistinguishable. Okay. So this is the case where, so just remember that this is the case where n, the number of data points, is relatively small, less than 30, and this is the case where n is bigger than 30, and I guess 30, you kind of flip a coin and choose which one you want. Okay? So those are the confidence intervals. Okay, let's have a look at an example. It's nothing too complicated here. So the idea, you have 7 data points. Apparently there are the contents of 7 similar containers of sulfuric acid, and they have, I don't know what these numbers mean, but the capacities, okay. So this is the capacities of these contents, okay, and we're asked to find a 95% confidence interval for the mean content of all containers, okay, and approximate, and we're assuming that basically the samples are approximately Gaussian distributed, or let's say they're not Gaussian distributed. Okay, so of course, in order to do this question, really all we want to do is we're calculating this confidence interval, okay, the left and right hand side of the inequalities, to the inequalities, and the key point is one has to be able to compute x bar and s, okay, and remember the formula for x bar is just the sum of the data divided by the number of data points, and the formula for s is 1 over n minus 1 of the sum of each data point subtracted by the mean squared. Okay, so that's how you're going to get those numbers. Okay, so n is little 7, and you can compute the mean and s squared. I'm very confident you can all do that without any difficulty. Okay, that's because you s squared. Okay, now what we're going to do, we need to find the value of t of 6 because n is 7, and 0.025 because it asks for a 95% confidence interval. So you should be able to do that, but let's have a look and remind ourselves how we can do that. So this is the F, there we are, T. So T is 6 degrees of freedom and 0.025, so by now you should be very straightforward for you all to do that. So apparently according to this particular table it's 2.4469. Okay, so we go back, and this is 2.447, so we've got it right. Somebody's got it right. So then the confidence interval is very straightforward to compute now. We're just substituting numbers into formula, so the confidence interval is x bar plus or minus 2.47 times s, which is the square root of 0.8 divided by the square root of 7. Okay, and that turns out to be, I don't think that's very complicated, that this population mean with a confidence level of 95% lies in this interval 9.738 and 10.262. So hopefully that's clear. Okay, so in example 2, so unsurprisingly, this is going to be the case where you use those Gaussian limits. So you have a department store, they're interested in estimating the average amount its credit card customers, which is pretty much everyone these days, spent on their first visit to the chain's new store in a given mall. Okay, so you have 50 credit card accounts are randomly sampled and analyzed, and you get the mean and the sample variance. It's just written down there. Very good. Okay, so there are 3 things that we want to do. Let's think about the first 2, and then we'll talk about the last one. So we want to work out the population the department store wants to learn about and the population parameter they want to estimate. Okay, well, let's think about it. Don't have to do anything too complicated. They're basically interested in studying all their credit card customers. Okay, so that's my population. And they want to work out, and so the answers in the question, all right, the average amount that the credit card customers are spending, so basically the thing that they're interested in is the population mean. Okay, so the answer to part A, the population is, it's all its credit card customers, and if you're a big shop like Tangs or I don't know, something like that, Harrods, that's a lot of people, so you haven't got time to, well, you probably don't have the resources even today, maybe you do, but Probably don't want to use all your resources to get all the information like that. And the average amount spent on their first visit to the chain's new store is the population parameter that they want, and mu. Okay. Now the last question is asking us to construct a 90% confidence interval for this parameter in part B. So of course here what we're going to do is going to use basically our second estimate, because that's what makes sense. So we're going to do this one. The reason we're going to do this one is twofold. If we assume that the population is normal or approximately normal, and we are not given the standard deviation or variance associated to these credit card customers, which we definitely don't know, then this is the confidence interval we're using, because the number of samples n is strictly bigger than 30, because it's 50. Okay, so that's what we're going to do, and alpha here is 0.1, so that's very much all we have to do. So this is the thing. So the estimate of this sample, the confidence interval is then going to be x bar plus or minus z, and z at 0.05, because alpha is 0.1 of s over root n, and we have x bar, we know s, we know n is 50, and z of 0.05 is 1.645. I'm sure that you know that. You can check the table for yourself this time. And so my 90% or our 90% confidence interval for the mean credit card expenditure on your first visit is around 57.9 to 67.2. I don't know what that is in dollars, I suppose. It doesn't say. It's dollars. Okay. All right. Okay, so that's that. So now what are we going to do? So now, of course, basically this whole chapter is just studying different ways to construct interval estimators for different population quantities. It's a bit myopic in some sense, but anyway, let's study it nonetheless. So in this case now, what we're going to do is to study a different scenario. So we looked at the case where we want one sample, and if you remember, if you look back in chapter 5, we studied two samples, and that's what we're going to do here. So now we're going to have two populations with means mu1, mu2, and variances sigma squared 1 and sigma squared 2. Okay? And on the basis of two independent random samples, i.e. two samples of size n1 and n2 respectively, of random variables x1 and xn1 IID and y1 up to yn2 IID, and we have realizations of that. So if you like, I just have two data sets and I'm considering them to be independent. Then what I'm trying to do in this particular part of the lecture notes is to construct confidence intervals precisely for the difference in the means of these populations. Okay, and of course you can consider many scenarios where one is interested in this. Okay, now how can one estimate the difference in the means? Well, we've already established in yesterday's lecture that the population mean is unbiasedly estimated by a random sample, which is the sample mean. Okay, and that similarly then, it's not unsurprising that if I take two independent random samples, that basically the difference in their sample means is precisely an unbiased estimator of the difference in the population means. And of course it is a point estimator by definition. Okay, it's a point estimator. I don't know. I can compute this for any collection of data set if my data set is not too huge. Okay, very good. Now, so now what I'm going to do, so now what we're going to do is we're going to think about some variety of situations. The first one is the simplest, which is that I take sigma squared 1 and sigma squared 2. The variances of these populations are assumed to be known, finite of course, and not equal. And the two populations are normal. Okay, right? Or if sigma squared 1 and sigma squared 2 are known and not equal, but n1 and n2 are pretty large. Okay. Well, okay, so the result that we're going to talk about, you can think about this as being in the exact case. So if you want to interpret what does that bullet point mean, so I'll just write it for you just so that you're very clear what this statement means, because we have so much time in the lecture course left that I can basically take my time and say whatever I like in some sense. So let's just make sure that we're clear what this first statement means. What we're doing is the following. I'm supposing that I have x1 dot 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 xn1, and these are where such that xi is IID, independent and identically distributed Gaussian, so we write n, and it has some mean mu1, and it has some variance sigma square 1, and it's known. Okay, so we know this. We put the red line here, so this is known. This is known. It's spelled known, sorry. Known. Getting late in the day, so that's known. Okay, so that's the x's, and then I have independently, so I write independently. I have a sequence y1 up to yn2, where the yi, again, are IID. They're normally distributed with a mean mu2 and have a variance sigma squared 2. Okay, and it's also known. Known, I can't spell known. Okay, this is also known. Okay, and sigma square 1 apparently is not allowed to be equal to sigma squared 2. Okay, this is what this first statement means. If you like mathematics, I like mathematics, that's why I've written it down. Otherwise, you can just read the words. That's basically an equivalent statement. Okay, so that's what the first one. The second one is very similar, except basically you're saying that n1 and n2 are large. Okay. And they don't have to be Gaussian. Okay, so of course the large part is justified by the fact that we have a central limit theorem. So a central limit theorem tells us precisely that we can basically work essentially with this scenario if these are big enough. Now, if you remember, if you go back to section 5.5, you can check it. We talked about it last week. The difference in the sample means is Gaussian distributed, and the mean of those means is mu1 minus mu2, and the variance of those variance of this difference is the sum of the variances when scaled by the sample size. Okay, that's a result. You can check it. We spent some time studying that. And why is this significant? Well, it's going to be useful because now we can derive a statistic associated to the difference in the population means, which guarantees that the probability of the coverage of the difference in the means is exactly equal to 1 minus alpha, i.e. we're going to provide another methodology to construct confidence intervals for the difference in the mean parameters. Okay? So we can assert, so where does this horrible looking equation come from? Well, it's this sentence here. So remember that I have x1 bar minus x2 bar, that's a number, right? That's just the average of the number of points in this x. I'm using x's, I'm using x and y, he's using x1, x2. I prefer x and y, but it doesn't matter. Okay, so this is the difference in the sample means is a number, so this is supposed to be Gaussian distributed. Okay, we know that if we take a random variable, which is mean mu and variance sigma squared, and we take that same random variable, we subtract the mean and scale by the standard deviation, that we get precisely a new random variable, which is again Gaussian distributed with 0 mean and unit variance. So basically, if I take this statistic, I subtract mu1 minus mu2, and I divide by the square root of this number, then the associated random variable is precisely standard Gaussian. Okay, and that's what he means, that's what he's done here. So this random variable here, is precisely standard Gaussian, and the probability that this lies between these two quantile values is exactly 1 minus alpha. So basically, the idea, very similarly to what we were just saying, let me just get rid of this thing here. Just again, the statement is basically, so if we define the statistic, so if I just say the statistic in that bracket here, so I call this Z, then basically the statement is essentially telling you, it's the same graph as I drew it right at the start of the lecture. You have this PDF, we have Z, we have Fz of Z, it's just a Gaussian. Okay, so the Gaussian, it looks like this, roughly. This is minus Z alpha over 2, Z of alpha over 2, sorry. Minus Z over 2, Z of alpha over 2 is supposed to be symmetric. Okay, this area here is alpha over 2, this area is alpha over 2, and basically the probability of the statistic lying in this interval then, this area here in the middle is 1 minus alpha. Okay, I said exactly the same thing just a few minutes ago. Okay. Now, because we know this, we're playing the same game as we've already done it twice before. Okay. Remember, in the statistic, we know sigma squared 1 and sigma squared 2, and apparently they're not equal. All we need to do now is to rearrange the equation inside the probability statement to get an inequality for mu1 and mu2, or the difference between the two, and then we can derive, hopefully, a confidence interval for the two associated, for the difference of those two parameters. Okay, and you can do it. It's exactly the same calculation as we did, well, almost the same calculation as this one. So here we are, we go back in time. So remember, we did these calculations, so these are always the same. Here, our denominator, or I'm pointing at the wrong thing here, this is s over root 10, so I multiply both sides by s over root 10, and I subtract mean and I multiply by -1, and I get something for mu. And if you play that same game here, what you'll get is your 100 times 1 minus alpha % confidence interval is going to be the difference in the sample means x bar minus x1 bar minus x2 bar plus or minus z alpha over 2 multiplied by this standard deviation, which is a square root of the one variance over its sample size plus the other variance over its sample size. Okay, and that's our confidence interval in this case. So let's see an example. It's not very difficult. I think you can study this really at A level. I don't know why we're doing it, but anyway. You have a study, you conduct it, you have two types of engines, A and B, and gas mileage, miles per gallon, was measured. Okay, very good. So you do 50 experiments with engine A, 75 for the other of engine B, and basically everything else is, all the conditions were held constant. I guess I don't know why that's so exciting. Oh, this is a lot of words. So the average gas mileage for 50 experiments using engine A was 36 miles per gallon. Okay, so we have our mean there. For the B, it was 42 miles per gallon, 75 experiments. Okay, so the basic information here, this is X1 bar, this is N1, this is X2 bar, this is N2. Okay, we want to find for change a 96% confidence interval on the difference between the mean of engine B and the mean of engine A. Okay, these are the average gas mileages for these two different types of engines. Okay, so you're trying to work out which one has better gas mileage. I suppose if you drive a car, this is important. Okay, and we're told explicitly that engine A has a standard deviation of 6. And engine B has a standard deviation of 8 miles per gallon, or gas mileage. Okay, so we have a lot of information. This is just substituting numbers into a formula. So we know the mean of type 1, type A is 36, and type B is 42. And a point estimate of the difference between those two means, remember it's B minus A rather non-intuitively, but it doesn't make a difference really. So that's 42 minus 36 is 6. And we know sigma 1, I don't know why he's writing 1 and 2, right? This is sigma A and this is sigma B, right? And alpha is 0.054. Why is it 0.04? We want a 96% confidence interval for some reason. Okay, so then we can find Z of 0.02. So just to give you an idea, I do know how to use these tables, even though I don't care about it. Where are we? The chi-squared. Let's see, where has we got this Z here? So 0.02. Z of 0.02. Okay. And then what do we want to do? So then, oh, no, 0.02. I want 0.02 here. Okay. Oh, very good. Yeah, we're about here. So it's 2 point something. All right, this is what it got, 2.05. Okay, so you can find it from the table. There's a bit of interpolation, but I don't know why you would want to do that. Okay, so now what we have, so now we want to find basically this confidence interval. So that's going to be the difference in the means, which was 6, plus or minus 2.05 times the square root. So this is the first variance divided by the sample, the number of samples. So the variance here was 8, so 64. And so here we have, oh goodness me, so this is 8 for B, and then you have 75. So you have 64 over 75. For this one is 6, so it's 36 over 50. Okay, those are the numbers there. So that's the formula you have to compute. So the difference of the mean of type engine B and A has a confidence interval at the level of 96%, which is between 3.4 and 8.5 miles per gallon. So what does that tell you? That tells you that basically B on average has more miles per gallon. So it's a better engine if you're interested in miles per gallon for your particular car or whatever you're using, truck. Okay, so now what are we going to study? So it's we're playing the same game, but so remember that what we have just studied is the scenario where precisely the number of the variance of these two samples are known. And of course, as you may understand, that in general you may not know this number unless it's a very strange scenario. So now we're going to study the scenario where basically the variance sigma squared 1 and sigma squared 2, we don't know these, okay? But that the number of data points in those two samples, A and B, or 1 and 2, are N1 and N2, and they're large, so they're order of 30 or at least. So then what you can do, and we're not justifying this, it's unfortunate we don't justify this. There is a theory to do that, but as usual, we don't tell you why. I'm just not sure why at this level we don't, but apparently we're not telling you why. That you can replace those two sample variances, those population variances, sigma squared 1 and those sigma squared 2, with their estimates, so the population variance S1 square and S2 square, with a normalization N minus 1. Okay, and if you do that, it turns out that this is providing you 100 1 minus alpha percentage confidence interval. So that basically the confidence interval is exactly the same as we were discussing in that previous example. The only difference that we're having is that instead of using those theoretical variances, so we had sigma squared 1 and sigma squared 2 in these two positions, under appropriate mathematical assumptions, which are basically the central limit theorem type result, that you can replace essentially those sample variances, those population variances with the sample variances. Okay, and that's what we're going to do. So there's no, again, I would like to justify these things, but we're apparently not allowed to do that. So example 2, so we have two kinds of thread being compared for strength. You can imagine that that is of interest. And so you've got basically two sample sizes of the same, two samples of the same size, so 50 pieces of each type. So N1 and N2 are equal to 50. So that type A has a mean, on average, we've got that 78.3, and the standard deviation is 5.6. And similarly, B is 87.2 and 6.3 respectively. And what we want to do is to construct a 95% confidence interval for the difference of the means. So basically, remember that we're just using this type of intervals for the difference of those two means, and the only thing that we really require is the Z value of the Gaussian. Okay, so basically we're given, okay, so we call them A and B, so X bar A is 78.3. X bar B is 87.2, so the difference of those means is minus 8.9. So again, what this really means from the beginning is we suspect that on average A has much less tensile strength than B. Okay, and we're already told the sample, these are the standard deviations, so these are just these are the two numbers here, 5.6 and 6.3. And basically we want a 95% confidence interval, so in this case you have 1.96 is our 95% quantiles. Okay, very good. Oh, sorry. And so then basically the solution is very much now very simple. The difference of the means was minus 8.9 plus or minus 1.96. This is the square of the standard deviation for the first one. The sample sizes are the same, so we got 50 here and 6.3 square here. And apparently that gives you a confidence interval for those differences of the order of minus 6.56 and minus 11.24. Okay, it's fairly straightforward. I think that's nothing too complicated there. Okay, so we're enumerating a lot of different scenarios, and I'm trying to make it as exciting as it is, but you can, but it's not very exciting, so there's not much more to say about that. So this situation is now the case where you don't know the variances, but you're assuming that they are equal. Okay, this is a kind of funny situation. It's really kind of a construct. This kind of statistics is a construct of what was done 50, 60 years ago when there was no computer, and you had to think about large sample sizes, and you had to think about approximate distributions, and you don't need to do that anymore, but still we teach it. So here what we're saying is that we don't know the variances, but those variances are precisely equal. Okay, so in this situation we're assuming again, I've removed it from the board, but basically now we have two independent we have two populations which are supposed to be different and independent, which are Gaussian, and we have small sample sizes. Okay, so the justification for these small sample sizes, big sample sizes, are really coming from the central limit theorem, which we learned last week. Okay, so in this situation what we're trying to do is we're again trying to study confidence intervals for the difference in the means of these two populations. And in order to do that, we again know that if we have populations which are normal, then basically the difference in the means are precisely Gaussian distributed, where the mean of this difference is the difference in the means of the populations, and the variance, well, this is the same result that we'd stated before. So when we started to study this thing, if you haven't forgotten, or if you have forgotten, we quoted this result. This was from chapter 5, and basically we're using the same result, except the only difference is that we're hypothesizing that these two variances, sigma square 1 and sigma square 2, are equal. Hence, this is why we have the statement of this result on the slide 55, 56. Now, that's why you get that wrong. Okay, so if you reverse engineer what we have studied so far. Okay, so again, playing the same trick as we have done. No, we have done it so many times, I don't think it's very, very difficult. So then this difference of these two sample means are Gaussian, with a mean mu1 minus 2 mu2 and a variance sigma squared times 1 over n1 plus 1 over n2. So now we take this random I take this random variable, I subtract mu1 minus mu2, I divide by the square root of this factor, and the associated statistic by the properties of the Gaussian distribution are precisely standard Gaussian. That is to say that this statistic is a standard normal random variable. Okay, and we have I've stated that. This is the fourth time I've said that today. Very good. Okay. So the key point now is that in this equation we do not know this factor. So remember, we're in this funny scenario where we have two independent samples. They have different means, but the variances are the same, but I don't know the variance. So I have to be able to produce an estimate of this. And it turns out that a good estimate, and there is a justification for the formula, is that you can use something called the pooled estimate of the variance. So the pooled estimate of the variance, sample variance, it looks like that. There is a justification for this formula, and again, apparently we don't teach you it. But basically this formula is just it's like a weighted average, right? So S1 squared, remember that's 1 over N1 minus 1, the sum over i's of xi minus x1 bar squared. And so you renormalize, so you multiply by this factor N1 minus 1, and then you divide by the total sample size minus 2. And again, there is a justification for this formula. Basically, this thing is chi-square. This is a chi-square on n1 plus n2 minus 2 degrees of freedom. Okay? So this is basically now, so what we're going to do is we're going to replace this sigma squared with this thing. Okay, it's still a measure of the variance, and it's a measure of the variance for the two variables. And basically this one is weighted essentially by the number of data points divided by the total number of data points minus 2, and this one is weighted as well in a similar fashion. Okay, now the key point is the following. So remember, okay, so remember that we have quoted this result, we discussed it in yesterday's lecture, that if you take S1 square, you renormalize by N1 minus 1, and you divide by this true variance, that's exactly distributed as a chi-square random variable on N1 minus 1 degrees of freedom. Now remember that intrinsic in our formulation is that these two populations are independent, so independently this statistic here is chi-square on N2 minus 1 degrees of freedom. It's exactly the result that we discussed in yesterday's lecture. We've discussed it, I believe. Okay, so basically now you can justify that this is the point is here. Let me just try to explain where this final result comes from. Okay, so the idea is this, right? You can easily prove this result if you were interested. I mean, we're going to spend our time, let's talk about it. So in this case, remember, so basically this first one, I tried to make this a bit more, so N1, I try to make it as big as possible, N1 minus 1 times S1 square is equal to sigma square. This is equal to the sum I is equal 1 to N1 minus 1 of Zi square. Well, it's equal in distribution, right? But you can say it's equal. Where the Zi's are IID, normal, naught 1. Right? This is the definition of a chi-square on N1 minus 1 degrees of freedom. Okay? So because we know this result that I'm pointing at, and hopefully you can say this is also true, that they're equal in distribution, but you can also say that there exists a collection of IID, normal, naught 1 random variables, and they're N1 minus 1 of them. So similarly, N2 minus 1 over sigma square times S2 square is equal in distribution to a sum, let's say I is equal to from 1 to N2 minus 1. And let's call these VI's square, where these VI's are IID, normal, naught 1 random variables. Okay, it's the same thing. Okay. Now the key point is now what I'm doing is I'm summing those two statistics. So I'm summing this statistic and I'm summing this statistic. Okay, that's what is done on the bottom line of this slide. So what does that mean? Well, what it means is, what's my point I'm trying to make? The point I'm trying to make is the sum of those two statistics. I'll just get rid of this part. The sum of those two statistics is equal in distribution. So I'll just call that statistic T, which is on the board, is equal in distribution to the sum I equal 1 to N1 minus 1 Zi square plus the sum I equals 1 to N2 minus 1 of the VI square. Okay, and this statistic, which I'm putting in blue brackets, basically this thing is precisely the definition of a chi-square distribution on N1 plus N2 minus 2 degrees of freedom. Okay, so this is why one can deduce this result on the basis of these two. Okay, so remember that these random variables here are independent of these. Okay, so these are all IID, normal, naught 1 random variables. This is the definition of a chi-square on N1 plus N2 minus 1 minus 2 degrees of freedom. Okay, so there is basically, why is that important? Well, we're going to see why it's important. Okay, so the key point is, right, what are we talking about? So let's go back to what we were talking about. Remember that basically this is our, well, not test statistic, but this is our statistic that we're going to use, and to invert this statistic in order to find a confidence interval precisely for the difference in the means. Okay, we don't know sigma squared, so we're replacing sigma squared with this SP square random variable. Okay, and this SP square random variable is not quite, but is related to this statistic. It's not exactly equal to this, but this statistic is chi-square on N1 plus N2 N1 plus N2 minus 2 degrees of freedom. So we remember that by definition a Gaussian divided by a square root of a chi-squared over its degrees of freedom is precisely a t distribution on n degrees of freedom, if n is the degrees of freedom of the chi-squared. So the key point is now, this is my, if I now renormalize this one by this one, and I multiply by sigma squared, then essentially this thing here becomes the square root of a chi-squared divided by its degrees of freedom, and this one becomes t on n1 plus n2 minus 2 degrees of freedom. Okay, so what's the point we're trying to make? Well, what we have done, okay, remember at the beginning we started with this statistic, but we don't know sigma squared, and we've got to this statistic, which we know everything in this formula except with respect to mu1 and mu2, and now we know the distribution of the statistic, and we're going to proceed as we did before. We're going to invert the statistic with respect to mu1 and mu2 to find a 1 minus alpha 100% confidence interval. Okay, and we're going to do that in 5 minutes time, so we'll have a break and we'll resume at 14:50. Okay, so let's resume. So we're talking about this statistic that we've derived, and now we're just going to. This is a standard procedure in this type of statistics. We invert the statistic as a function of the parameters to find the confidence interval. So let's do it. So it's the same thing. So basically, we know that the statistic is t-distributed on n1 plus n2 minus 2 degrees of freedom. So the probability it lies between those two quantiles, I've drawn a graph associated to this twice, so I think you're clear on what this thing means. The probability that the statistic lies in this interval under the fact that the mean is, the data are random, is precisely equal to 1 minus alpha. Okay, that's very good. Now what does that mean? Well, we invert now this to get our 101 minus alpha percent confidence interval for the difference in the means. It's the same thing that we're doing again. So as per usual, what you do, you multiply both sides of this inequality by this quantity, you subtract this thing, and you multiply by -1. And basically now our confidence interval is the difference in the sample means plus or minus that t quantile multiplied by the pooled variance multiplied by square root 1 over n1 plus n2. So this is a confidence interval for the difference in the means where the sample sizes are small and the fact that the variances of the two populations are assumed to be equal, and they are normally distributed. Okay, there's a lot of assumptions in here. So the reason that, by the way, if you're wondering why there are a lot of assumptions on the sample sizes or they're small or large, is because basically in order to get these type of probabilities, okay, I'm trying to guarantee that the probability that the parameter of interest lies in the interval is 1 minus alpha. I need to know something about a distribution of the statistic, okay, and that's why we're making those assumptions. If you're wondering why do we say large sample size, small sample size, independent, so on and so forth, that is why, okay. Okay, so SB was the school's pooled estimate, and we know that these are the quantiles, okay. I don't think we need to explain this. We've already explained this one so many times that we should know what it means. Note that basically for larger sample sizes, so remember the point is that once you have larger sample sizes, the difference between this value and this value is they're arbitrarily close, okay? So what you can do is if the sample sizes, both of them are bigger than, say, 30 respectively, then basically you replace this with this, okay? And then the estimate becomes, for larger sample sizes, basically the same statistic, except I've replaced this with this. Okay? Hopefully that's clear. Okay, let's look at an example. So a course is taught to 12 students, by a conventional classroom procedure. So that's group 1, that's our first group. Our second group is going to have size 10, and they are going to be the same course by programmed materials. I guess maybe this is an old example. Maybe you've got a flipped classroom for one, and or not a flipped classroom, maybe you've got online materials. So this is basically like a test for this class where you've got 25 people that come to the lecture, and the other set, if they do, they watch it on the lecture on video. Okay. So at the end of the examination, these people are given the same examination. Okay, that's what we hope for. And the 12 students who were in the classroom had an average grade of 85 with a standard deviation of 4. Okay, and the other ones had 81 with a standard deviation of 5. And we want to find a 90% confidence intervals for the difference in the population mean. So the average value of the scores of the two type of students, one of which went to the class and the other of which went and watched everything on video. Okay, and we're assuming that basically both of the populations are normal samples, and that basically they have the same variances. Okay, well, that's not so unreasonable in this example, I think. So again, we represent by mu1 and mu2 respectively the grades of people who take this course. Basically, mu1 is the average value of the people in the classroom, mu2 is the average value of the grade for those who were watching on video. Okay, and we know that the observed value of those, the difference between the sample means, so one was 85 and the other one's 81, so that's 4. So that's a point estimate for the difference. And now we're assuming, remember, that the variances are equal, so we want to compute the pooled estimate of our population variance. Okay, so the pooled estimate, remember, so we have 5 is the standard deviation, so I have 25 here and I have 16 here. So then the pooled estimate is going to be 16 multiplied by n minus 1, which was 11, sorry. 25 times 10 minus 1 is 9. Then I have n1 plus n2 is 10 plus 12, 22, minus 2 is 20. Okay, so the pooled variance turns out to be 20.05 if you put those numbers into a calculator. You don't need that here. So there are 90% confidence interval. So now we're using the t distribution because our sample sizes are small. They're 12 and 10 respectively. So we have a t distribution on 20 degrees of freedom. We want a 90% confidence interval, so we want 0.05 here. Okay, so this difference in the means, we've computed those. We've got these numbers from the tables and the pooled variance, we've just computed them. And these n1s and n2s are 12 and 10 respectively. Okay, so basically now what we have is our confidence intervals is 4 plus or minus 1.7247 times square root of 20.05, and then these are the square root of 1 over n1 plus 1 over n2. Okay, and the t on the t distribution, remember, is t on 20.05. So if you like, we can compute that. Let's see if we can find this. Chi-square is the t, so t is, what was it, 0.05, t on 20, 0.05 is about 1.7247, and that's what he's using here, 1.7247, okay? So the confidence interval, if you plug in the numbers, you get basically the difference in the means is quite variant. Basically, on average, they could be as much as 7, but at least 0.69. Okay, so basically what that means is, on average, we expect that basically the class 1, i.e. the students that went to the class, are seen to be doing better on average than the people that watched on the video. We'll see if that's true for this one. Okay, very good. So what's underlied our data, or basically our random variables of study, or our two samples in so far, has been the case that basically the individuals, the random variables associated to the groups, are independent, right? So we're assuming, for example, in our in this example, that basically the students who go to the class and the students that go to the watch the video are independent, which is not reasonable in some sense, because, well, we're assuming that here, although it may not be reasonable in practice. But in some scenarios, it might be that you basically have samples which are intrinsically dependent, okay? So, for example, in this situation, you're having a test on the new diet of 15 individuals. So this is before and after, so I'm sure you've all seen these adverts of people that go and take some new weight loss scheme, and they go in and perhaps they're a bit slightly overweight, and then they come out and they're all very magically thin. So this is an example where basically the weight of the individual before the treatment and after the treatment is primarily, there must be some dependence between those two things. Otherwise, it's kind of a bit funny. And this is the scenario that we're going to look at. I don't think, again, this is a little bit not very modern, because I don't think that, well, I don't know, these weight loss programs are perhaps becoming politically incorrect. But anyway, basically these two samples are made on the same individual, and there is a relationship between them. So there is basically paired samples. Okay, so basically the random variables before and after are kind of correlated. So in this scenario, what we're going to do is we're going to work with the difference, okay? So we work at the random variables, so the population variable is a difference, and then what we're observing are essentially differences which are supposed to be independent and identically distributed, but because we model the difference instead of the random variables themselves, somehow our life is a little bit easier. Okay? So this is, as you said, so basically the setup is, so again, if you want to understand properly what's going on, so let me just write things down. You can read the slide and have a think about whether you understand it or not, and I'll write some things and hopefully everything will be clear after that. That's the worst whiteboard I've ever used. Okay, so the idea is that you have now the model is this. So you have a random sample. So the idea is you're modeling. So you have a collection of individuals D1, D2, dot up to D. Let's say N, or we're using N, and these are going to be IID with some mean and some variance. Okay. So this is the setup, okay? So there's a population difference, which you're trying to estimate. Perhaps you're trying to work out the population mean of the difference, or you're trying to work out the variance of the population difference. And the scheme is that you're going to obtain IID realizations of the differences. So in our example, the differences which you realize are the before and after, the difference between the before and after weight of the individual that's gone through this weight loss program. Okay. So we're going to assume that they are Gaussian distributed. Okay, sorry, I forgot to write that down. So this is IID normally distributed with mean mu d, and variance is sigma squared d. Okay, and this is the population that we're trying to estimate. Okay, now we can do that. It's very easy. So now this is actually once you've put this framework, the framework of this thing, the dependence is somehow kind of, it's a way of avoiding the dependence. So instead of thinking about, well, I have to model the dependence between the before and after weight, once you model the differences, you go back, to the situation that we had before, essentially. So you can estimate the difference in the means between those two groups, which are correlated, using basically, you record the differences, the before and after, and you compute the average. Okay, that's very easy. You can see the formulas in front of you. And if you want to compute precisely the variance of this thing, the variance is, again, in the same way. You have basically 1 over n minus 1, and your data, the differences now. It's very simple. Okay, so these are giving you 2-point estimates of the mean and the variance of the difference. Okay, very good. Now, what do we know? So now let's have a look at ways we can construct 101 minus alpha % confidence intervals for the mean of the difference and the just the mean of the difference for now. Okay, so define the statistic capital T. Okay, so where is this coming from? So you look at this capital T, and I define that to be d bar minus mu d over sd over root n. Okay, and we claim that's T on n minus 1 degrees of freedom. And you ask me, where has this come from? What am I talking about? Well, we talked about this. I'm going the wrong way. No, I'm going the right way. We talked about this right almost at the start of the day's lecture, I hope. No. We've done so much stuff today that I've... So this is essentially where we started. This is where we started today, and we said basically x bar minus mu s over root n, n is small. The xi's are a normal population. This is T on n minus 1 degrees of freedom. The difference between the scenario that we're studying now here and the study that we studied right at the beginning of the lecture is almost identical. It's in fact identical. The point is that all we're doing is we're replacing the x's with the d's. So these have a different conceptual interpretation as being differences of dependent samples, but they are still assumed to be IID normal mu d sigma squared d random variables. So basically I can just replace, instead of having x bar, I write d bar, and instead of writing s, I write s sub d, and I have the same result. Because basically the underlying assumptions of the result, which is written in this slide, is no different from the scenario which we're currently studying. Okay. I forgot what page I'm on. What did I get to? Okay, we're getting there. Where are we? There we are. Okay, so this is precisely where this result comes from. So now when we've defined the statistic, if I want to find 101 minus alpha % confidence interval for the difference, or the average difference of these dependent samples, then basically I can use this capital T as what is called a pivot in this literature, and you invert the pivot. So it's the same scheme. Basically, I multiply these two quantiles by SD over root n, I subtract d bar and multiply by -1, and so my 101 minus alpha percentage confidence interval for the differences of these dependent values are precisely d bar plus or minus tn minus 1 over 2, tn minus 1 alpha over 2, where alpha is the level of confidence, multiplied by sd over square root of n. Okay, so the situation is different that you're modeling, but the distributional assumptions to derive the associated pivot slash statistic and its inversion are identical to the scenario that we studied right at the beginning of today's lecture. Okay, and as we said, remember here what we're saying. Where did I say that? We didn't say that. We said that basically the number of data are small. I didn't say that. Where did we say that? This is exact. Okay, so if n, the number of samples, gets large, right, then of course what we do in this confidence interval constructor is instead of this one, we use z of alpha over 2, right? Because basically this number and this number for n relatively large, at least 30, basically those numbers are almost indistinguishable. So that's what we do if the sample size is large. Okay, so here n is large. Okay, let's have a look at an example. It's quite nice. You have 20 students, and they're divided into 10 pairs. Each member of the pair has approximately the same IQ. Okay, IQ is a very subjective thing, but let's suppose we can do that. So one of each pair is selected at random, and assigned. One of each pair is selected at random, and they're either going to be math or they're going to be programmed, assigned to a math section or program materials only, and the other one is basically going to do go to the class, apparently. So at the end of the semester, each group is given the same examination, and the following results were recorded. Okay, so what are the results? Okay, so you have those 10 pairs. Okay, and you basically have people that go to PM, means programmed material, and lecture is lecture, okay, and they have these scores in their tests, okay. So we have 76, 81, blah, 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 all the way up to 88 and 83. And we have the differences in their scores, okay. So basically the key point is that the two individuals that you're using, they have almost the same IQ. So if IQ is the only thing which is relevant for taking exams, and believe me, it's not, then basically the pairs of scores should be dependent in some way. Okay. So basically the point is, now what we're doing is, instead of worrying about how do we model the score of the first individual, how do we model the score of the second individual, and then work with the difference, we model precisely these differences. Now what we're doing is we're assuming that these things are basically IID, normal, mu d, sigma squared d. And now what we want to do is we want to construct a confidence interval for the difference in the means, which is just mu d. Okay. It's asked for a 98% confidence interval. Okay. So this is pretty straightforward. Why is it straightforward? Because now we have dealt the confidence interval. We've got this, just going to compute d bar and the standard deviation, okay, and that's it. Life is done, because this tn minus 1, so n is 10, so we have n minus 1, and it's 96% confidence interval, I think. Is that 96? 98, oh, good God. So then alpha is 0.02, so alpha 2 over 2 is 0.01. Okay, so now from the data you can compute the mean and the standard deviation. I'm pretty sure you can do those. That is not a difficult thing to do. Okay, you can do that, I don't know, very straightforwardly. So apparently the average value is minus 1.9, minus 1.6, and the standard deviation squared, the variance is 40.71. And so alpha is 0.02, so this doesn't imply, alpha equal 0.02 doesn't imply this, okay, but it's if alpha is equal to 0.02, one can calculate T9 0.01 if you want. We can use the tables, since I'm forced to use them. So what was it? 9 0.01. Okay, so apparently it should be 2.8214. 2.281. What is it talking about? T9 0.01. This is 9. This is 0.11. Somebody is wrong here. 9 0.01. 9, 0.01. He has a mistake in his lecture notes. I think the table is correct. I don't understand how he's got that. Anyway, so this is not 2.281. It should be this thing that I've labeled here. This is T degrees of freedom, 9 and 0.01. According to this table, 8 or 9? I can't. Yeah, no, 8 is 9. So it should be 2.8214. Okay, so there's a mistake in there. Okay, so there's 98% confidence interval. Okay, so just d bar plus or minus t on 9, 0.01 times sd square root of 10. Okay, so if this number is correct, 2.821. Yes, he's got it. He's just got this one the wrong way around. Okay, so this is 2.821. Let's take a statistical table. Oh, I've lost my lecture notes now. 2.821. Right, so I got it right. I was right. Okay, so the confidence interval for the difference in the means is minus 7.29 and 4.09. Okay, very good. So, okay, so we're moving on. Let's have a look at, well, I mean, I can finish it today, but I think we can spare a bit more slowly. Okay. I don't think we're going to go further than example 1 today. So let's see if we can get there. And if we don't, then it doesn't matter. Okay, so that was the case of paired data. Now let's have a look at the case where we want to compute confidence intervals for variances. So essentially what we have done in the last hour or so is to exhaust essentially all the situations you can think of with our current knowledge to construct pivots, i.e. statistics, associated to population parameters and invert them in order to find confidence intervals precisely for those quantities. Now what we're going to do is to look at producing a confidence interval for a normal population where we're considering the ratio of the variances, okay? Again, the point here is that what we're going to do is we're going to use, well, you hear ratio, what you think about is F distributions, and I suspect this is what we're going to do here. I've forgotten already. So in this situation, we have x1 up to xn, our random sample of size n from a Gaussian. Okay, so basically, as we have written on the board, except instead of using d's, you use x's, and approximately means that if n is large, we're getting exactly that, and if n is larger, things are good, or let's say they're exactly. So the sample variance, it can be used as a point estimator for sigma squared. We know that. We've said that 1,000 times. We worked out that this was an unbiased estimator of sigma squared yesterday, so we can use it as a point estimator if you like. That's fine. I'm not going to do anything there. It's very simple to show this formula. I will not show that for you. Okay. Now let's suppose we know the mean of the data. So if we know the mean of the data, we know that for any data point xi, if we standardize it, so any replicate xi, we know that xi minus mu over sigma is normal naught 1. Okay, that's true for every I in a set 1 to n. Okay, I've mentioned this standardization result frequently today. Okay, so we know that a standardized Gaussian random variable, when I square it, I get a chi-square 1. Okay, I had written some blurb on the board just about an hour ago, which just told you about that. Okay, so now if I take the sum I is 1 to n of this thing, this statistic, I get a chi-square on n degrees of freedom. Okay, that's basically the definition. We had seen that when we defined the chi-square on n, and we have seen it earlier today. Okay, right. Therefore, if I look at this statistic, so what am I doing here? What we're doing here, the strategy is always the same. I want to find, in this case, I'm trying to find a confidence interval for sigma squared. That's why it says ratios, when they're variances. We're starting with variances, okay? So I have this statistic. I know the distribution of this statistic, okay? Now the key point is now, because it's a function of sigma squared and I know mu, I can invert this statistic precisely in order to obtain a confidence interval for sigma squared. It's always the same scheme. I construct a statistic, I know the distribution of the statistic, I try and rearrange an interval in terms of the quantiles of the underlying distribution of the statistic, which allows me to construct my 101 minus alpha percentage confidence interval. It's really a method in statistics. Okay, so basically what this thing means, okay, so the thing is, as I wrote twice before, except this case, this is a chi-square distribution. So remember, in this case, sigma squared is a non-negative variable. Well, not variable, sigma squared is a constant. Okay, so these quantiles are for positive values. Okay, so basically we have this, right, and so then basically we can invert this. We divide both sides of this equation by the sum I is equal 1 to n of the xi minus mu squared, okay, and then we invert, okay, so that is to say, okay, if you're wondering where does this inequality come from, I'm sure you can do the calculation, but since it's not so super clear, okay, so basically what this inequality is you have basically, so you have the big P, the probability, I'm going to use like that because I prefer that notation. So you have the probability, so we have chi square, this is n minus 1 minus alpha over 2. And that's less than the statistic, which is the sum I is equal 1 to n of xi's minus mu squared. I can put 1 over sigma squared here. And that's less than chi square n minus 1 alpha over 2. Okay, and that's equal to 1 minus alpha. Okay, so you can remember these values we discussed them in yesterday's lecture, I believe. Okay, so now what do? I can divide this statistic. So if I'm going to call this y because my handwriting is very bad, so I'll just call this y. So this is equal to the probability that chi square n minus 1 minus alpha over 2, and you divide by y, is less than 1 over sigma square is less than chi square n minus 1 alpha over 2 divided by y. Okay? And then basically to complete these calculations, I have 1 over sigma squared, so I now invert, so I do 1 over, and if I do 1 over, I flip this inequality around. So that's been basically the probability that sigma squared, I'll put this like this, so I now have to flip this one around, so I have y over chi square n minus, n, what is it, n? Oh, it's not n minus 1, I just was writing n minus 1, sorry, it's n. Sorry about that, it's n. Well, I think you know that I was just making that mistake. So that's y over chi square n alpha less than sigma square less than y over chi square n 1 minus alpha over 2. It's alpha or alpha 2? It's alpha 2. Alpha over 2, sorry about that. Alpha over 2. And that's equal to 1 minus alpha. So the justification is basically, so this is the first line. So if you can't read it, maybe you can't, but it doesn't matter. This is the first line, is just basically this line. And all I'm doing is I'm just rearranging this equation in order to get to this thing here. Hopefully it's relative. Y is that statistic, and I just don't want to keep on writing y. Okay, so basically what is this? This is a 101 minus alpha percentage confidence interval of for the sample variance. Okay, so it's not an unreasonable thing to want to have to know about. If you estimate the variance, I want to have a confidence interval for the estimate of my variance, which could be the sample variance itself, and this is in a confidence interval, which may or may not contain the sample variance, depending on alpha. So that's the I mean, basically, this is just a restatement. But I critically have to know mu, the sample mean, which obviously is not it's not a fantastic assumption, because typically we don't know the sample mean, the population mean, excuse me. Okay, very good. Okay, so let's have a look at this. So if mu is unknown, we know, well, this is, at least we know something. We've learned this today, and we learned this, we knew this for a while, that if we take the sample variance, we scale it by n minus 1, and I divide by the true variance. Okay, that's basically this, the sum I is 1 to n of xi minus x bar squared over sigma squared. We know that's chi squared n minus 1 under our assumption. So remember that we learnt this When did we learn this? We learned the chi-square n minus 1 degrees of freedom. So this result, I think we have quoted it today, although I'm beginning to forget I'm beginning to forget it. But this is what we had quoted earlier today. Okay. So the key point is now what we have constructed in this particular scenario is precisely a statistic which is a function of sigma squared. So this is a statistic which is a function of sigma squared. I don't know sigma squared, but again, I can use it as a potential pivot because I know the underlying distribution of this statistic. And because I know the underlying distribution of the statistic, I can construct or attempt to construct a confidence interval if I know the associated quantiles, of which I do because we have tables for this, or I know them up to some numerical error. Okay, so it's the same procedure. We know that the probability that this statistic lies between this alpha and 1 minus alpha over 2 confidence intervals, these points, is have probability 1 minus alpha. Remember that this is basically the upper point and this is the lower point. Okay, right? And so basically now if you rearrange, so basically you multiply, so you divide both sides of this inequality by n minus 1 s squared and you take to the power minus 1. So basically the same procedure that I did here. The difference is that this statistic is now x bar. Okay, so now x bar, so then basically I get the same calculations here, which is the same. You can see the same. This statistic is very similar. The confidence interval was very similar to the thing we did before. Then our 101 minus alpha percentage confidence interval for sigma squared is clearly just going to be this is the upper value, lower value, and this is the lower value. Okay, so that's our 101 minus alpha percent confidence interval. It's the same logic as here. The only difference is that this is a seemingly useless procedure because we do not know the value of mu. Okay, but remember that what we're doing here is we lose, basically it's the same thing. We've just lost 1 degree of freedom up to some thing that we had before. Okay, it looks this should look very familiar to the case where you know the mean, because basically this thing, s squared, is very similar to the statistic is very similar to what you had. All you've done is you've replaced the population mean with the sample mean, and you've lost a degree of freedom in those quantiles. Okay. Okay. What am I doing here? Yes, and this is the remark that I made. The degrees of freedom have gone from n to n minus 1. Okay, and the logic for that is because you've estimated the mean mu, although there's some more things to think about that. Okay, so as I promised, this is the last part. I could finish the lecture notes today, but I think we've got so much time that we're going to just finish up this example now. So the following is, you have the volume in deciliters of 10 cans of peaches, okay, distributed by a certain company. And we want to find a 95% confidence interval for the variance, all cans of peaches which are distributed by this company. And we're assuming basically these are, as we had started from the beginning, IID, normal mu sigma square random variables. Okay, so you can compute the sample variance. Okay, that's 1 over 9. The sum I is 1 to 10 of the xi squared minus nx bar squared. That's the formula which I decided not to verify for you. That's 0.286 currently. So from the statistical tables, let's check if he's right this time. I've managed to get rid of my statistical table. Let's just open it up again. So chi squared. So our chi squared is where? That's just f. The chi squared is this where. Okay, so this is our chi squared table. So we want chi squared 9, 0.025. So 0.025 chi squared is apparently 19.028. I think that's right. 19.023. Well, it's not too far off this one time. And chi squared 9, 0.975. Okay, so let's do it. We're here, 0.975. 9 is 2.7004. 2.7. Good. Okay, so that's it. That's all we need. We need s squared. We need those two chi square values, and we're done. Because basically now we multiply s squared by n minus 1, and we divide by that chi square n minus 1 of alpha over 2. And similarly here it's pretty much the same, except we have this different value of the quantile. And so basically the 95% confidence interval for sigma squared is that it should be between, we're 95% confident that it is in the region 0.135 and 0.54. Okay. And that's, well, I mean, I'm happy to continue on. I mean, we could finish it today, but I think that it's best to do, to leave it to next week. The key point here is that the difference is going to be that you're going to be computing ratios of chi-squares, which is going to give you essentially an F distribution. I mean, that's all. Okay, so that's it for today. So we will resume chapter 6 next week. Most likely we'll be very close to completing these lecture notes within a week and a half or so. I have some extra material which I will teach will be non-examinable, and then basically to conclude the course I will be going through some exams to make sure that you're ready for the exam in I think it's May. We may finish a couple of weeks early, but I think that's probably a good thing. So thanks very much for your attention. I'll see you on Thursday of next week.